Good morning, everyone. Myself, Uday Ranjan Goud, working as Assistant Professor in Department of Aeronautical Engineering, MLR Institute of Technology. So, in the previous session, we discussed about shear center of closed section beams, in which we found out how to determine shear center for a given closed section beam. Now, in the present module, we are going to discuss about torsion of open and closed section beams. The learning outcomes in this module are: at the end of this module, the students are able to analyze open section beams and the students are able to analyze closed section beams subjected to torsion. Now, to understand this torsion of open section beams, we are trying to consider a thin rectangular strip as shown in figure A, and in which the torsion is applied, and this is a thin wall beam which we considered. So now here, torsion, let's try to understand this diagram. So a thin rectangular strip we considered, and let us consider one small element in this, and which is of having depth delta S, and magnifying this small element and redrawing that in the right side diagram, which is shown in figure B. And so it is an approximation of element, and in which the shear lines are clearly depicted over here in this diagram. So if you look at this one, and there are two axis system we are considering, one is S direction and other one is N direction, and in which you can look at the shearing lines, the shearing action that is drawn over here. Now, from this element, we try to deduce the formulas which are related to torsion of thin-walled open section beams. Now, so if such a strip is bent to form an open section beam as shown in figure A, and if the distance S measured around the cross section which is large as compared with the thickness T, then the contours of the membrane, that is the lines of shear stress, are still approximately parallel to the inner and outer boundaries. So that you can understand from the diagram. Now this beam is bent, and in which we considered one small element, and if you look at the shearing action, that is the shear lines, so they are almost approximately same like what is shown here, even if the curve is bent. So it follows that the shear lines in an element delta S of the open section beam must be nearly the same as in an element delta Y of a rectangular strip, and which is demonstrated in figure B. So the curved beam, even if you bent a curved beam is bent into the curved manner, and even the shear lines look similar like as shown in the figure B. Now let's try to, and for this the maximum shear stress is given by tau Zs maximum, that is equals to plus or minus gt into d theta by dz, where d theta by dz is nothing but the rate of twist, and G is the capital G is the modulus of rigidity, and T is the thickness of the beam. Now we know from torsion formula, like rate of twist, we have the torsion formula like T by J equals to tau by R equals to G theta by L. So from here we have the rate of twist formula, and which is nothing but G theta by dz, and here you can write torque, that is equals to Gj into theta by L, in which you can write this Gj into theta by L, you can write it as d theta by dz, that is twist per unit length. So the rate of twist is expressed in terms of the applied torque and is given by T equals to Gj into d theta by dz, and the shear stress distribution and the maximum shear stress is sometimes expressed more conveniently in terms of the applied torque. So the maximum shear stress which we have here, and it will be expressed like this, that is tau Zs equals to 2n by j into T, or maximum shear stress, that is tau Zs maximum is equals to plus or minus T into capital T divided by J. So this is the formula which we are going to use for the open section beams which are subjected to torsion, that is the maximum shear stress. So the formula one is this formula, tau equals to torque equals to Gj into d theta by dz, and the maximum shear stress we are going to use this formula. So these two formulae will be used for the torsion of open section beams. Now moving on from torsion of open section beams to torsion of closed section beams, and The torsion of closed section beams, which you can see here, and you are considering one arbitrary cross section like this, which is shown in figure, and in which again you have axis system, x, y, z axis system, and we are going to apply the torques on the z axis. So you can see here equal and opposite torques that are applied. Okay, so that when you apply torque on this particular shaft, and it's going to twist. So a closed section beam which is subjected to a pure torque as shown in figure, and it does not, in the absence of actual constraint, develop a direct stress system. So it follows that the equilibrium conditions of equations are reduces to dou q by dou s equal to 0 and dou q by dou z equals to 0. That is the shear flow per intensity, that is equal to 0. Now for this closed section beam, and the application of a pure torque of a closed section beam results in the development of a constant shear flow in the beam wall. The relationship between the applied torque and this constant shear flow, that is applied torque T, and the constant shear flow, that is Q, is derived by considering the torsional equilibrium of the section as shown in figure. So now what we are doing here, we are just taking one tangent to this arbitrary section, and let us assume that Q as the shear flow, and in this you consider one small element in this one, and let the width of that element will be delta s, and let us consider the distance from distance P, which is nothing but the distance from the origin to the tangent, which is drawn here, and then you consider one small element, and then that is through origin you consider one small element whose width is delta s, and now here the torque T is applied. So we are trying to reduce the relationship between applied torque T and the shear flow, that is Q. So the torque produced by the shear flow acting on an element ds of the beam wall, that is the PQ into ds, that is given by, now the area if you try to do here, and here Q into ds you can consider as area, and then multiply by the perpendicular distance. So this is nothing but P into Q into ds. So the torque is given by, and this is only for the one element, and if you try to apply for the complete arbitrary cross section, so you can write T equals to cyclic integral of PQ into ds, and also integral PDS. PDS is nothing but the area, and integral PDS can be written as 2a, and therefore replacing integral PDS by 2a, we are going to get T equals to 2aq. So this is very important relationship that we got, that is torque is equals to 2aq. Okay, so T equals to 2aq, and which will be used in the problems, that is torsion. So for example, if the this is only for one arbitrary section we considered. Now if you have two cells, or if you have three cells like this, cell 1, cell 2 and cell 3, then this equation can be extended, like you can write it as 2a1q1 plus 2a2q2 plus 2a3q3 and so on. Okay, so that is a torsion equation what we have in the closed section beam, and this theory is called as Bredt-Bateau theory of torsion. Okay, and is often referred to as Bredt-Bateau formula. So T equals to 2aq is called as Bredt-Bateau formula, and the rate of twist also given from this expression, that is rate of twist is given by d theta by dz, and that is equals to q by 2a cyclic integral of ds by gt, where q is the shear flow, a is the area of the cross section, and g is the modulus of rigidity, and t is the thickness. Okay, or you can write in terms of in other words also, that is you can write the rate of twist in terms of torque also as q equals to 4a square cyclic integral of ds divided by gt, by considering t equals to 2aq, so that you can replace q equals to t by 2a, and when you substitute t equals to q equals to t by 2a in this equation, you are going to get this equation. So these are alternate forms of rate of twist, that is d theta by dz. Okay, so after knowing this formula, let's try to consider one problem, and probably we'll look into it how to solve the problems on torsion of open closed section beams. So a thin walled circular section beam has a diameter of 200 mm and length is 2 meter long, and is firmly restrained against rotation at each end. Okay, and a concentrated torque of 30 kN is applied to the beam, at its mid-span point, and if the maximum shear stress in the beam is limited to 200 Newton per mm square and the maximum angle of twist is limited to 2 degrees, calculate the minimum thickness of the beam walls, and he has given modulus of rigidity as 25,000 Newton per mm square. So let's quickly look into this problem, and what is given. First of all, he has given diameter, that is equals to 200 mm, and then length is also given 2 meters. Again, you need to convert this into mm, so this will become 2000 mm. And then he has mentioned that is firmly restrained against rotational region, that means both the ends are fixed. And he mentioned that a concentrated torque of 30 kilonewton meter is applied to the beam at its mid-span. So this is very important to understand, that if you consider a shaft and then a concentrated torque is applied at the mid-span, that is 30 kilonewton meter. Okay, so if the torque is applied at mid-span 30 kilonewton meter, then if you try to find out reaction for this, and you are going to get the torque, that is here you can consider the maximum torque applied at the ends will be 15 kilonewton meter each, 15 kilonewton meter and 15 kilonewton meter. Okay, so then the maximum, and what is given here, maximum shear stress he has given, that is tau max he has given, which is equals to 200 Newton per mm square. And then the maximum angle of twist, that is theta max, is also given, that is equals to 2 degrees, and modulus of rigidity he has given 25,000 Newton per mm square. And then he is asking to calculate what is the minimum thickness, that is T minimum equals to what. So for this calculation of the minimum thickness, and he has given two conditions for us. One condition is the maximum shear stress condition, and second condition is the maximum angle of twist condition. So we'll have to look into these two to find out the minimum thickness of the beam wall. So the minimum thickness of the beam wall corresponding to the maximum allowable shear stress 200 Newton per mm square is obtained directly, in which the maximum, that is just now we have seen 30 kilonewton meter is applied at the center, so that the maximum torque that can be applied is nothing but what, 15 kilonewton meter. Again, we will convert this into Newton per mm. So 15 into 10 to the power of 3 for 1 kilo, and then another 10 to the power of 3 for converting meter into mm. So 15 into 10 to the power of 6 Newton mm is the maximum torque. Okay, so now let's try to apply the formula, that is the maximum, that is what we have here. It is T equals to 2aq. Okay, and then we can write this in terms of 2a into q, you can write in terms of maximum shear stress, that is you can write it as tau into T, and therefore that is equals to torque. And from here you can write T equals to capital T divided by 2a, that is if you want minimum thickness, and the shear stress should be maximum. And therefore you substitute here, and we know that the torque is nothing but 15 into 10 to the power of 6 that we have seen, and 2 into area, and since it is a shaft, then you can write it as area of the shaft, so the circular cross section, that is pi d square by 4, and therefore pi into diameter is 200 square divided by 4, and the maximum shear stress is limited to 200 mm. So if you try to calculate this, you are going to get minimum thickness according to the maximum shear stress condition, that is equals to 1.2. Okay, so now we'll try to look at into the other one, that is the rate of twist. So the rate of twist, because here you are given two conditions, one is the maximum rate of maximum shear stress condition, and we calculated minimum thickness according to that, and now we need to check the minimum thickness according to the maximum angle of twist condition. So to know that, we are going to look into rate of twist first. So the rate of twist along the beam is given by, and we know the formula that we have seen in the previous slide, that is d theta by dz. So the rate of twist that is given by q by 2a cyclic integral of ds by gt, or d theta by dz equals to 4a square cyclic integral of ds by gt. Now the same formula here we are going to use, d theta by dz equals to t by 4a square cyclic integral of ds by gt. Okay, so this formula we are going to use, and since the modulus of rigidity he has given as constant, then you can write it as 4a square g, and then we have left with cyclic integral of ds by t. Okay, now Coming to here, cyclic integral of ds by t. Now this cyclic integral of ds by t is nothing but ds is nothing but the circumference, that is the total length of the beam, so that you can, since it is a circular cross section, that is a shaft, so that you can use pi into d as the circumference. So pi into diameter, and thickness you can write as it is t minimum. So by substituting cyclic integral of ds by t here, you are going to get t by 4 a square g into pi into 200 divided by t minimum. Okay. Now since this is the rate of twist, and we need to integrate this, and what we need to do here, it is taking the origin for z of the one of the fixed end of the beam and integrating this equation 1 for half of the length of the beam. Then we obtain, when you try to integrate, d theta by dz becomes t theta, and t 4 a square g, rest all these things will be remain constant, and then pi into 200 by t minimum also remains constant, and then you get z, because you are differentiating with respect to z, plus a constant c1. So that is what it's shown here. Theta equals to t by 4 a square g into 200 pi by t minimum into z plus c1. So we need to evaluate this constant of integration by substituting its boundary conditions. So since he mentioned that both the ends are fixed, and at the fixed end where z equal to 0, the rotation, that is the slope, that is the twist, is also 0. And when you substitute in this equation, you are going to get c1 equal to 0, and then you left with the similar equation, that is theta equals to 4 divided by t divided by 4 a square g into 200 pi by t minimum into z. And since for us in the question given data, the maximum angle of twist is given as 2 degrees. So now we need to convert this into radians. So you can convert this by multiplying pi by 180. So now for substituting theta max as 2 into pi divided by 180, and let's try to substitute in the formulae. And also z, since we are considering at the mid span, so total span is 2 meters, and you can consider at mid span z equal to 1 meter, again in which you can convert this 1 meter into 1000 mm. So you can write 1000 mm and then substituting here. So therefore theta minimum, that is equals to, so what you are going to get here, it is t into 200 pi into z divided by 4 a square g into theta max. So this is what we need to substitute. So when you try to substitute for this one, and the torque is again taken as 15 into 10 to the power of 6, and then 200 into pi into z is 1000 and divided by 4 a square. So a square is pi by 4 d square, and when you try to square it, you get pi square by 16 into 200 square into g is 25,000 into theta max, and that you need to use 2 into pi divided by 180. So that 180 you can add here. So overall it is shown here 15 into 10 power 6, 200 pi into 1 into 10 power 3 into 180, that is 2 pi by 180 into 4, and area is pi by 4 d square, and since you have area square, so you're going to square it, and then modulus of rigidity is 25,000. And when you calculate this, you're going to get the minimum thickness as 2.7 mm. So here we got two minimum thicknesses values, and one is from the maximum shear stress condition. We got a minimum thickness should be 1.2 mm, and whereas from the maximum angle of twist condition, we got that the minimum thickness should be 2.7 mm. So, and since we need to consider the allowable thickness that satisfy both the conditions, and if you consider 1.2 mm, then this is not valid, or if you consider this one, then this is also can be valid. So therefore, if you consider the minimum allowable thickness as 2.7 mm, it satisfies both the conditions of maximum shear stress as well as the maximum angle of twist. So therefore, the minimum thickness can be considered as 2.7 mm for this case. Okay, so this is how we calculate the problems, that is minimum thickness in the shear flow, that is torsion of open and closed section beams. Okay, so this is how we try to solve the problem. So mostly when it considered for torsion of closed section beams, we are going to use the two formulae. One is the T equals to 2aq, and the second formula, that is rate of twist d theta by dz equals to T by 4a square cyclic integral of ds by gt. Okay, so that's all from the today's session, and we will meet in the next session for the combined open and closed section beams. Thank you.